let me try to explain that in a very simple terms. For that, to understand electrical impedance spectroscopy and how it's incorporated in the food application in our project, let me explain you how the gas sensor works. So basically, the gas sensors which we are using for the food freshness detection have a sensing layer which is sensitive to the gases, and it's sensitive to a wide range of gases which are emitted during the food spoilage process. So how we use it is that we give some voltage across it and try to measure what is the current flowing through that sensor, and that current is basically faces the changes in it when you are exposed that sensing layer to the gases. Okay, now in generally we use that sensing layer with what we called as DC voltage, which is like a fixed voltage. It's not changing, you just apply some voltage, you keep on measuring what is the change in the passing current inside that sensor when it is being exposed to the gases. Now in electrical impedance spectroscopy, we try to look it into a different way. What we are doing is, instead of applying a fixed kind of a voltage, we say, okay, let's apply some kind of a changing voltage into it. And those changing voltages can be of different frequencies. So basically, it can be changing at different rates. In electrical impedance spectroscopy, the idea is that you give that same sensor, the same sensing layer, the voltages of changing voltages of different frequencies, a broad range of frequencies, and see where you find the maximum response out of the sensor, that is the maximum change of the passing current corresponding to the gases that are being emitted by the food spoilage. That's how electrical impedance spectroscopy we plan to use for food freshness detection. Basically, there are two elements in this project. One is the food, and the second is the sensors. Okay, the food emits gases, and I recently explained that the sensor experiences change in the passing current inside it, corresponding to those gases. There is some kind of a relationship, but how are we going to understand what is actually that relationship? So that can only be understood by artificial intelligence. So the role of artificial intelligence in this project, in a very simple term, is to understand that relationship between the emission of the gases and the changes in the sensing layer in a better way, so that we explicitly know when particular stage of spoilage occurred, and which results in a particular spoilage or particular emission of gases, where are we in the spoilage process. That is the role of AI. This is basically the two targets of my PhD. First is, one is that which I first explained, the role of AI is to basically create the relationship between the sensor response and the gases emission, right? Now, to get the very good prediction of spoilage process, you need to enhance both of the technologies. One is the sensing layer itself, which is actually giving you the response or the change in the current. The electrical impedance spectroscopy potentially can give us more information, or I would say better information out of the sensor. And once you have better or more, in technical terms we call higher dimensional information, AI can do a better job. So basically, combining these two technologies can create a solution which will be good in both sensing and actually making sense out of that sensing information.